So in the last video we have developed the equation for the strain along the x-axis, which one is a function of y, is given as minus y divided by rho, where rho is the radius of curvature, and the maximum strain is given as c divided by rho, where c is a larger of y distance from the neutral axis of either from the top fiber or from bottom fiber. So if we consider this cross section here, the top fiber is away from the neutral axis, and therefore this was a larger distance as compared to the bottom fiber from the neutral axis. And in general, if I substitute for rho in equation 1, I get the strain along the x direction, which one is a function of y, is equal to maximum strain multiplied by minus y divided by c. Now here one of the assumption is that the material we are using is a elastic material. So if we draw a diagram of the stress versus strain, and we have the elastic limit is up to SYT. So in the elastic limit here, the Young modulus is given as the stress divided by strain. So the type of material used is elastic, and therefore we can very well use the Young modulus equal to stress divided by strain. Now here we can define the value of the stress. So we can get the value of stress as a product of Young modulus multiplied by the strain, that equal to epsilon. So if equation 4 is multiplied both sides by the Young modulus E, then we can get here the generalized expression for a bending stress. So we have a strain along the x direction, which one is a function of y, is multiplied by Young modulus E, will be same as the maximum strain epsilon max multiplied by the Young modulus E, and is further multiplied by minus y divided by the distance c. The product of a strain multiplied by Young modulus is nothing but the stress. So the left hand side product here, the epsilon multiplied by Young modulus at any distance y, will be the bending stress, that is sigma x, which one is a function of y, equal to epsilon max multiplied by E, same as equal to the maximum bending stress, will write as sigma max multiplied by the vertical distance y divided by the c, the larger distance between the neutral axis and either top fiber or bottom fiber. Now the value of the sigma max is remain constant here, the value of c is remain constant. It means that we have bending stress, which one is a function of y, is directly proportional to the distance y, that is a negative of y. So there is a linear relationship between the bending stress and the vertical distance y. So we have to set up our axis system at centroid. Horizontal axis will be x and vertical axis equal to y. According to that, we have to show the distribution here. So this one is our equation number 5. Using this equation, we can show the distribution of a stress for the given cross section. So we'll use the same cross section here. If I put the value of y is equal to c, in that case I will get the given value of sigma x will be equal to sigma max, but negative value. So we have a reference line here, and from this reference line we have compressive stress. Compressive stress will show on the leftward. So we'll mark this value, and this value will be same as the negative value of sigma maximum. And if you see the bottom here, bottom at a certain distance here, so this bottom distance will be less than c, is same as equal to sigma x at bottom fiber. And if I put here the value of y is equal to 0, we are exactly at neutral axis. And when we have y is equal to 0, we have bending stress will be equal to 0. So the bending stress distribution will be shown as in this figure, and since we have bending stress at any distance y is a linear function of y, so we have a straight line distribution shape. And at neutral axis we have bending stress is 0. As the value of y will go on decreasing, the value of the bending stress will also go on decreasing. So this is exactly the bending stress distribution in the case of a section where the section is unsymmetrical. And we assume here the value of m is positive. So from the neutral axis, if we show any distance y from the neutral axis, that is at this distance y, we have corresponding value of bending stress is sigma x, which one is a function of y, and is given as minus of sigma maximum multiplied by y divided by c. So this will be the tension value and this will be the compression value. So we have successfully developed the equation for the strain along the x direction, which one is minus y by rho, as well as we have successfully developed the equation for the strain along the x direction as a function of y, which is same as equal to the maximum strain multiplied by minus y by c. And in the similar way, we have a stress, that is a bending stress at distance y, which one is a function of y is equal to maximum bending stress multiplied by minus y by c. Bending stress we have defined, the strain we defined, now we have to define the moment. Now we're going to develop the equation for the bending moment m. For this one, we'll show here the three-dimensional view of the given cross section. So this figure represents here the three-dimensional view of the given cross section. We have the length of the trapezoid at the top end is a smaller and bottom is a larger. So with reference to certain reference here, we'll measure the x location of the given cross section and we'll mark here the centroid that equal to g, and this axis here is our neutral axis. So this axis is same as our neutral axis equal to NA. And the bending stress distribution is shown here at any distance y. We have bending stress is a function of y is given as negative value of sigma max into y by c. Now as far as the moment is considered, a moment is given as the force multiplied by the perpendicular distance. Let's say here perpendicular distance is d, and the force is given as the stress multiplied by area multiplied by perpendicular distance. So we'll consider here one element at a distance equal to y from the neutral axis. So let's consider here this elemental area at a distance equal to y from the neutral axis. And at this point here, the stress is acting equal to minus of sigma max into y by c. So let's represent here that this small strip has the area equal to dA. It's a very small strip over which we have the bending stress is remain constant. So we know the value of the stress that equal to sigma x. We know the area equal to dA. So for this element we can calculate here the force F. And this force F above the neutral axis is acting at a perpendicular distance equal to y. So we can calculate here the bending moment for this given element. And the height of this differential element will be equal to dy. So this area multiplied by sigma x will be the elemental force dF, which is acting perpendicular to this plane. So let's show here that this element will exert a force and whose direction is shown like this. So this one is a force equal to dF, which will act at distance equal to y. So we can calculate the value of dF here, that is the force exerted on the elemental area. And we are able to calculate this force dF value as a product of stress multiplied by area. And stress we have is a stress along the x direction with a function of y. So in this case we can write the value of dF is same as equal to sigma x, which one is a function of y multiplied by the area dA. And we can very well replace the value of the bending stress, which one is a function of y, as a maximum stress multiplied by y divided by c. So in this case we have dF will be same as equal to minus of maximum stress multiplied by y divided by c, and is further multiplied by elemental area dA. And this force is acting at distance equal to y, so it will develop a bending moment. That will be equal to the force multiplied by perpendicular distance. This time the perpendicular distance is y. Now recall that in our original figure we have taken the case of sagging, and this bending moment was taken as positive value, as well as this one is also taken as positive value. So because of sagging here, this one is the direction of m and this value of m is positive, whereas the force about the neutral axis will make a clockwise moment and anti-clockwise moment is taken as positive. So we have counterclockwise will be taken as positive for our discussion. So this moment that will be generated by force is a clockwise, and therefore you have to take this moment as a negative moment. If we show the bending moment m in an anti-clockwise sense, then only we have a compressive stress on the top and the bottom we have tensile. So right now we have dm will be represented here the moment, that is a bending moment about the neutral axis Na for the given element. And this value of dm is clockwise, whereas counterclockwise we have taken positive. So we'll treat this value of a dm, and minus sign is because of clockwise, is df multiplied by y. Already we got the equation of df as minus sigma max into y by c multiplied by dA. So we have a differential bending moment for the differential area dm can be written as minus, and minus become positive, is sigma max is positive sigma max divided by c. This value of y and this value of y will be y square multiplied by dA. Now if you want to calculate here the total value, we have to integrate this equation. So we have integral of dm is same as equal to value of sigma max, and c is a constant value that will not change, so that will take it outside. We have sigma max divided by c, and we have integral y square dA. Now this integral y square dA is called as the second moment of area about the z-axis. So you have to take the second moment of area about the z-axis, that will replace as the term Iz, and we have to integrate this over the entire area. So generalized equation will write as suffix equal to a, and here also we'll write here suffix equal to a. So total moment will be equal to m is same as equal to, so this bending moment is again taking place about the z-axis, so I will give the additional suffix as mz, and we have maximum stress, that is the maximum bending stress divided by the maximum distance c multiplied by Iz, where Iz is second moment of area about the z-axis, or sometimes is also called as the moment of inertia. So if you know the value of the bending moment, in that case you are able to calculate the value of maximum bending stress if you know the value of Iz. So you must be familiar with the second moment of area about the z-axis for all sections. We may have a rectangular section, circular section, a trapezoidal section, T section, I section. So that basic requirement here is to calculate the value of bending stress. So we have developed the equation for maximum stress here. So we have maximum bending stress. I will use the symbol sigma b maximum is same as equal to mz, that is the bending moment about the z-axis divided by the moment of inertia about the z-axis multiplied by constant c. So remember this equation. The last equation we have number 5, so this one is equation number 6, and we can substitute here for sigma max from equation 6 into equation 5. So let's substitute here. In that case we can calculate the bending stress at any distance y will be equal to sigma maximum, which is same as equal to m divided by I. When I write here default, it means that our z-axis multiplied by constant c and multiplied by minus y by c, minus y by c. So c and c will be cancelled out, and we have bending stress at any distance y will be equal to m into y divided by I. So we have forget to write here negative sign. So we have bending stress at any distance y is given as minus m into y by I. So as far as the equation number 6 is considered, we have bending stress is entirely dependent on the value of m. If the bending moment is positive, bending stress is positive, and if the value of m is negative, then the bending stress will be negative. Secondly, we have bending stress at any distance y is given as m into c by I minus y by c. So bending stress at any distance is given as minus m into y by I. Distance y you have to always measure from neutral axis, so you have to set up our system in this fashion. And if we combine the results 6 and 7, in that case we have m by I. So instead of mz and Iz, I will write m by I is equal to sigma maximum, that is the maximum bending stress divided by c, and is same as equal to minus of bending stress at any distance y divided by the distance y which is measured from neutral axis as per this coordinate system. The strain along the x direction, which is a function of y, is given as minus y by rho, and we have Young modulus is the strain along the x direction, which one is a function of y, divided by strain along the x direction, which one is a function of y. Now here I will substitute for the strain along the x direction, which one is a function of y, from equation 1, which is minus y by rho, where rho is the radius of curvature. So from equation 1, we'll get the egg modulus is equal to stress along the x direction, which is the bending stress, which is the function of y, divided by minus y by rho. So it is minus y divided by the radius of curvature. This radius of curvature will shift in numerator and then will come in the denominator of egg modulus. So we have egg modulus divided by the radius of curvature rho will be same as equal to the bending stress, which one is a function of y divided by y and is a negative value. So let's say this one is equation number 9. So 8 and 9, if we combine, then we'll get the bending moment m divided by I. Remember, it's about the z-axis is same as equal to the maximum value of the bending stress divided by c is same as the bending stress at any distance y, and we have to take the distance y from the neutral axis, and it's a negative sign, and this negative sign of bending stress divided by y is same as E by rho. So on the right hand side we have E divided by the radius of curvature rho. So this one is a famous Flexure formula, that is we have bending moment about the z-axis divided by moment of inertia about the z-axis is the maximum bending stress divided by c is same as equal to the bending stress at any distance y but negative value divided by y, where distance y you have to measure according to the coordinate system, where we have to set the origin at G, vertical axis is y and the horizontal axis is x, is same as the egg modulus divided by rho, where rho is the radius of curvature. Now one question has to be answered is that is the neutral axis really passing through the centroid or somewhere else? So we want to show here that the neutral axis is passes through the centroid. So we'll consider here the same element that equal to area equal to dA at a distance equal to y from the neutral axis. Position of G will not show right now. We'll just show here neutral axis because we want to prove here that the neutral axis will pass through the center of gravity. So position of G is not shown. So this stress acting at distance equal to y is given as maximum stress multiplied by y divided by c is a negative value, and if you multiply it by the area, then we can calculate here that total force equal to dF. But as far as the pure bending is considered, the shear force equal to 0, it means that the sum of all this force must equal to 0. So for pure bending, the total force F along the x direction must equal to 0. And we can compute this value as the elemental force dF. So we have integral of dF, which is same as the integral of the stress x, which one is a function of y multiplied by area dA. And we can replace the value of the stress at any distance y as integral of minus of sigma max, which one is a constant value, divided by c is a constant value, multiplied by y multiplied by dA. So this one is the total force, and this total force must equal to 0. So if you solve this integral, in that case we have minus of sigma max by c. Minus sign is meaningless because on the right hand side we have 0. So we left here with the maximum bending stress divided by c, and we have integral y dA. Integral y dA is the first moment of area is equal to 0. Now the bending stress cannot be 0, that is true. So maximum bending stress cannot be 0. Secondly, the value of c cannot be 0. It means that the integral y dA must equal to 0. And the standard solution of integral y dA is area multiplied by y bar, where y bar will represent the centroid distance. So this integral we can write as a into y bar. So this product must equal to 0. But this product is 0, it means that either area should be 0, but area cannot be 0. It means that the value of y bar must equal to 0. Value of y bar is 0 only when the neutral axis will pass through, the neutral axis must pass through the centroid. So it is compulsory here that a neutral axis should pass through the centroid. In that case we have y bar equal to 0. and therefore it is proved here. So neutral axis must pass through the centroid of the given cross section area. So this one is our cross section area, somewhat like this. This one is our x-axis and we have y-axis. So since we have set up our original system, the system at origin, so value of y bar will be 0 as well as x bar is also 0. So this is just a proof here that the neutral axis must pass through the center of gravity. And this one is a very useful equation, which one is bending moment. The moment of inertia is a maximum bending stress divided by c is equal to minus of bending stress at any distance y divided by the distance y from the neutral axis is equal to E divided by rho, where E is the angle modulus, rho is the radius of curvature, y is the distance measured from the neutral axis along the y direction, c is the maximum distance of the top fiber or bottom fiber measured from the neutral axis. And the value of m can be positive or value of m can be negative depending upon we are sagging. Sagging means we have smiley face, and whenever we are sagging, in that case the value of m will be positive, and if we have a hogging, then we have m is negative. So bending stress can be positive or negative. It depends upon the value of m, that is the bending moment. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.